All right, so, all right. Lord, we just thank you for the students that are able to come to class today. And we totally understand if they are having internet connection issues, and we just pray for the safety of all the residents near or that have been affected by the hurricane and the hurricanes that are Maria that's heading our way. And we just pray for everyone's safety, and that anyone that does not get to come to class today will be able to watch the audio at some point and the recording and be able to grasp all the concepts that we talk about. And it's in your name we pray. Amen. Okay, so what I want to do, I was going to go on to parallel circuits today, and we might do that, but I felt like after I got your experiments and stuff and some questions about the calculations, and as crazy as it kind of was last week with the hurricane going through, I thought we should definitely go over our series circuits again just to make sure that we absolutely understand our series circuits before we move on. Colton, it didn't say to take a picture. Always take a picture. I won't count off. I'm sorry, buddy. I may not have put that on there. All right. I will fix that. Yes, for next time. Thank you for telling me. Okay, so we're going to go through our experiments and our questions that we were supposed to answer for series circuits. Just look at a couple of different pictures that we didn't get to see last week and some that we did look at, but can't hurt us to look at it one more time. So we know that this makes sense. The higher the voltage, the higher the current. The lower the voltage, lower the current, and that just makes sense, okay? Then when we look at resistance and current, let's look at these two items. Here's our little symbol. Let me get a different color. Our horseshoe. And here's our symbol of a resistor if we were drawing a schematic, right? The more resistance, in other words, if you're playing tug of war here, you're both pulling, then lower the current, okay? If you have a lower resistance, I love this picture. She's like, here you go. Then that group right here is going to win, right? They're going to have the higher current, okay? So keeping those things in mind, we want to make sure, like t-shirt guy, yeah, some strong guys here. We want to make sure that we understand the difference between higher resistance, lower resistance, and higher voltage, lower voltage, and what happens with the current, okay? The current is those free electrons that are trying to get through all the wires, all right? They're trying to get through. Here they are, running, 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 okay? So let's go through our questions that we had. I want you to text me some answers. Let's clear off the board here. There we go. All right, here we go. Number one. The pathway for electrical current is called a what? A, B, C, or D? Good job. Circuit. Number two. When the electrical current cannot flow, the circuit is what? You could say broken, but that's not the best answer. We have a specific word for it. Specific word. It's called open. Yes, broke, but it's open. Actually, it's not necessarily broken because if you closed it, it would work. We're assuming it's a circuit that would work if you closed the switch. But I could see where you would put broken. That's silly. All right, number three. What are the positive and negative ends of the battery called? Great work. Battery terminals. Seems like they're all being A. This is crazy. All right, number four. Objects that allow electrical current to flow are called a fancy name here. There you go. Conductors. Good work. B. Number five. Get ready. Get ready. The unit that measures a battery's strength is called what? Yeah. How many volts? And we worked on that some with your experiment that you had to do, and we're going to talk about those calculations today as well. All right, a couple more questions. Number 6 is right here. A device that opens and closes a circuit is a what? Opens it and closes it. Good work, everybody. D, yes, yes. All right, number 7. The series circuit with 2 batteries is going to give how much voltage to a light bulb? So remember, our batteries, they were all 1.5, right? So if we have 2 batteries, we add that together and get 3 volts. Good work. Yes, I'm going to show pictures. Yes, we're going to go over the experiments. Noah. Yes. All right, number 8. 2 main things needed to maintain electric current flowing are what? Very good. That was a joke question there. A. All right, number 9. How many volts are in the batteries that we have used? Each battery, 1 battery. Ooh, you know what I just noticed? That could be a typo. I'm going to have to go back and check. I just realized this has the V beside it and that one does not. It should be C, but technically it does say the word volts here, so let me write myself a note to check on number 9. All right. Typo. Last question. A series circuit is formed when be careful what it says. A says there's 2 or more loads connected end to end and there is only multiple paths for current to flow. That's not true. B says 2 or more loads are connected end to end and there is no path. Oh, that's not going to work. C says 2 or more loads are connected end to end and there's only 1 path. Yes. Good work. Got to read all the answer choices, okay? Always read all the answer choices. Now, use your noggin. I want you to think. What's going to happen if you increase the voltage? So you're increasing the batteries. What is the current going to do? Is it going to increase or is it going to decrease? Current's going to go faster, right? Increase. Increase, yes. Okay, number 2. If you decrease, that means you're going to stop the resistance. So that's going to allow the current to flow really good, right? So it's going to increase. There's 2 ways that we've increased the current here. Now, if, number 3, if the current increases, if you get the current going faster, what is going to happen to the resistance? Yes, D. Decrease. Good job. If the voltage, all right, is decreased, the battery's decreased, what's going to happen to the current? Is it going to increase or decrease? Yep, decrease. Good job, guys. And the last one, the current is decreasing, then the voltage would be decreased. You guys are so smart. Okay, what we used on our series circuits experiments was our resistors. And if you happen to lose a resistor, you can always use a piece of tinfoil. Let me go down. I want us to look at our experiments before we do this. Hold on. Let me scroll down. Here we go. I didn't have that many because I didn't have many people give me their picture because I didn't say to. This was Cole's information. And, okay, Diana. And actually, Cole, you got it all right. That was very good. I think whenever where's my paper? When I calculated this one, it was 6 point, where did it go? 0.63829, and it kept going. So very good. We just needed to, you rounded it to the hundreds, but you could have rounded it to the tenths. So that would be an okay answer. And you had to use a calculator, right, to get that. So what we do, here's your formula. We simply divided 3 divided by our resistor, which was 4.7. We were not using anything. We weren't using the light bulb. Colton, you don't want to make sure yours either, okay? And so we just divided 3 divided by 4.7. Got the right answer. All right. Let me see who else does I have. So Colton and Zion, no. Let me see this. It's okay. That's why we're going to go over it, because some people did get this part wrong. So I feel like I need to explain it again. Yes, that would be me wanting to go over it. Here's Daniel's. That was a very good picture. Awesome. Landon. I don't think Landon's here yet. There's Landon's picture. Very good work. All right, Noah's. Good picture here for Noah. Has both of his light bulbs going. Awesome. Did I already show Cole's? Oh, there's Cole's. I had his paper and his picture on different pages. So the light bulb is lighting up, and you can see the resistor here really good. That's a good picture. It's hard to see it. It's so tiny. Yep. Yeah, when I'm clicking it so fast to put it in there, sometimes it's okay. That's all right. You did good. Okay, so here's what I want us to do. And Zion said don't show his. Okay. I'm going to give you a website. Let me please go up. Give me just a second. I got us out of order. There it is. Okay, I'm going to give you this link. Now listen, before I give it to you, got to make sure you understand. Look at the screen for a moment. The first thing you're going to do is pick your battery. So just everybody when you get the link in a minute, pick 1.5 volts. And you're going to drag it to either this circle or this one. If it goes back, that means you drag it to the wrong circle, okay? So you want to put it in the right spot. Then start with your 5 ohm, or maybe that was 3, I can't see that far, bulb, and put it in the other circle, okay? Once you're done, then there'll be a place for you to scroll down, and you would think about how many, calculating the current, how many amps it would be. And once you pick a number, you click the switch, and you'll see if it will work, okay? Once you get it, it'll make more sense to you. In other words, I want you to kind of play around with it, and then we can fill in our data table. I have a data table here that we can fill in for some different amounts, okay? If we can get it to work, let me get you the link. This is an awesome website. Okay, here comes the link. All right, click that. I love the way when you put it into the diagram, when you build the circuit, then look at the picture below, the diagram below, the schematic below, and it shows you what you're doing. It's really cool. So let me change my screen in here. Go back. All right, so if we do the 1.5 for the first one, tell me, if anybody wants to tell me what they get for their resistance, which is the light bulb, right? And it gives you the answer. Let's see what it has. 5 ohms for that first one. Go back. Somebody tell me what will work. Got 0. All right, pick a different number. Yep, if it didn't work, then take your current, go back to that drop down, Zion, and pick a different number. All right, what did you get, Bill, to make it not blow up, but the light bulb worked? 3, yay! 0.3. It's 0.3. That's supposed to be a decimal. Good work, guys. Okay, so let me go back to my screen. Let's pick a different battery. You want to try the 3-volt battery and see what you can do with it? You can't get the page to load. Isn't working. Okay. Does it say it's loading, Virgil? Colton, does it say it's loading? Does it say you need Adobe or Adobe Flash? Okay, see if you can click it. It'll have a little picture, and it should load then. Oh, Cole has new sound. Okay. Yep, never mind. Okay. All right, so let's do this. I will be sure. This is a really awesome website. Let me see. We've got time to do this. Let's try this. Pull it up. Go. Tell you what, y'all close the tab. It's loading now. If you close it, I can put it in the classroom. And that way we can at least see a few of them together. Oh, you got it? Okay. All right, so Virgil, waiting on yours. If you're in Chrome, it seems to go slower. So I just take the link and I'll copy it and put it in Firefox. Or if you're using Internet Explorer. Okay, so Colton has it working. Virgil. Yes. Thank you, Lord. Okay, so play around with it for a minute. We'll fill in our table here. I know some of you have already gone past us. We were going to try, let me go back and see my screen. We were going to try the 3-volt, right? 3-volt battery. And then pick which light bulb you want to try. You could try the 5 and see what happens. See if anything happens. Might work. Test it out. It's really cool because you don't really blow an actual bulb here. See if mine's not letting me drag it again. Sometimes it does that. Noah was typing something for us. Noah, did you get a calculation that worked when you was the fun with for nothing? Okay. Who was it that blew 2 bulbs? I forgot. Virgil, maybe? Yeah. And so he had to order 2 more. I hate that happened. I know. Well, we don't want to blow both of them. Then you got to buy another one. Try not to. But it is fun. You're right. Okay. Did anybody get a 3-volt with 5 ohms? I used my calculator. 3 divided by 5.6. Did it work? Thanks, Bill. Okay. So is there another one that you tried? Did anybody try? I had to close mine out. Let me look at my paper copy. What do we have? A 6-volt and a 9-volt. Did anybody try 6-volt or 9-volt yet? And tell us what something they got. Try a 6-volt and see which one of the bulbs you can light up. Yeah, sure. I had to close my virtual lab because it was freezing and I didn't want to freeze the classroom. So if you can, this is just your little time of exploring. See what you get. So we're going to try the 6 volt. You could try the 9. Yep. And then see what your resistance is. Try 9 volt. It lit up to 25. Okay. 24. Okay. It blew up. Good job, Noah. Pretty cool. Yeah. I know. Oh, yours won't light? Okay. So what do you need to do? You might need a lower battery or a higher wattage bulb, right? A higher resistance bulb. See if you can figure out which one will work. They all will work at some configuration, though. We have to make sure that we have everything, the right volts, going with the right bulb. Yep. Or it will blow, just like in a real light switch at your house. Yeah. And it could cause a fire, which wouldn't be good. Yeah, you can blow it up on the website, sure. Absolutely. Blow it up, yep. It's pretty cool, yeah. Very good. All right, Zion, tell me if you got it to work. Did you get it with the 6 or the 9? Not yet. Okay, it's all right. Let me give you, how about 2 more minutes? Let me see here. I'm going to go up. I have another really cool one we're going to do. Sometimes it goes really slow here. $1.8. Which volt are you using, Zion? Let me show you some configurations that I've done in the past that do work. Come on, please go down. Okay. So here's some, 9 volt. Okay, what did work? Here's some ones that did work. We already checked that one, this one. We checked that. The 6 volt will work with 5 ohms. That one works. Shows you the amperage, okay? And then the 9 volt, excuse me, with the 5 ohms. All right, did you try it with the 15? Noah did. What did you get, Noah? I have it here, and looks like we did not calculate it yet. Yep. So let me use my calculator here. 9 divided by, what did you get 9 divided by 15? 0.6, I think. Yep, so the current would be 0.6. Yeah, 0.6 or 0.60 exactly. Good. Same thing. That's a 6. Yes. Now, okay, so all of these, I'm sorry that printed like, I don't know why when I upload stuff, sometimes it's just crooked. This all should be in this column. That's weird. Whenever we're doing our calculation to get our current or our amps, okay, that's all we do is we take the voltage divided by the resistance. Here's our formula down at the bottom. Yep, the voltage total divided by the resistance total. Yes. Now, we haven't talked about how to calculate our wattage or the power, okay? And to do that, once again, you're just using a formula. To find it, you're going to take whatever you got for the amp amount and multiply it times the voltage, A times V. So, for example, this one right here, the third one. We had 1.2 for our amp. I'm going to multiply that times my voltage, which was 6. And that gives you the wattage of that specific configuration. You didn't have to do that for your experiment or anything. That's just something extra. What I really need you to know about is the voltage, resistance, and current. Okay, these three are our most important ones that we're talking about right now. Okay, go ahead and will you close that link with the wonderful experimenting virtually. And we're going to do a quick matching game. I'm skipping around a little bit because I want to make sure we don't lose our time. So what is an electric current? I will give you that link. I'll put it in the classroom, in the Power School. What do you think this one is, electric current? Steady exchange of electrons moving, exactly. All right, so for the next one, conductors, they allow, right? They allow things to move. Yeah, you want to draw? All right, no. Draw some lines. Make sure you close that other tab. Because if you don't, you know it might mess up this classroom or your classroom. All right, Noah, draw some lines for insulators. And how about static electricity? I don't see a line. Check your color. Weird. There it comes. Okay, I had to just click. Oh, wait, it's gone now. Did you click erase? I just saw it was green. That's weird. All right, hold on. Let me take away the drawing and see if this works. Okay. I don't know what happened. All right, so insulators here, and then amps is the unit of measure. That's what we figure out when we're calculating the current. Good, good. All right, let's do some calculating. Since we did that really good. Okay. So when we're trying to figure out the resistance for a series circuit, we just simply add it all up. So for letter A, what is the total resistance from point 1 to point 3? So we just want this part. Text me what you think that is. So we just add. Look what we add now. Only from point 1 to point 3. So we're adding the 5 and the 20. I know y'all can add. Yes. 25. Good job. All right, how about the next one? They want, be careful, they want the points from what? Point 2 to point 4. So find that section. Point 2 is here to point 4. So we would add up the 20 and the 15. Good job. Yes. 35. Awesome. All right, how about the last one? We want the total resistance from points 1 to 4. So that's all of them. from point 1 to point 4. Add them all up. There you go. Good job. Awesome. Very good. 40. Okay. Now, we're still talking about our, come back here. Okay. We're still talking about our series circuits, okay? Remember, it's one path, okay? One path. So now, I want to go ahead and just show you how we would calculate these items, like some of you did for your series circuits, which was very good. If we have labeled our resistors here in our picture, we have a 10 ohm resistor, a 20, and then a 30, okay? So, there's only 2 cells, there's only 2 batteries. As the current is moving, it's going to go through all of the resistors, right? So we want to calculate, we simply calculate using the amount of voltage, and then what is our formula? Right here. You take the voltage total and divide by your resistance. So that gives us our current. And that's what you guys were doing on your series circuits for this past week. Now let's look at our voltage in a series. Go right here. What happens to the voltage in a series and how is it calculated? So a lot of times, oh, you're fine, Dale. It's okay. I'm glad you came back. As voltage moves electrons through resistance, the electromotive force is used up as they're moving, okay? And you're going to have a voltage drop. It's going to vary according to what resistance or what load is slowing it down. And then what happens is something that's called Kirchhoff's second law. I have a picture for you. We talked about this a little bit last week. If you see that right here, this is a 6-volt set of batteries or battery, okay? So as the current moves, this particular resistor is going to take 2 volts, correct? This resistor right here is going to also take 2 volts. This one is going to take 2 volts. So if I add that up, 2 plus 2 plus 2, I should get the total that is applied from the batteries. 6. Good job, Zion. Exactly. Who died when he was 63? Gustav? Did you look that up, Noah? Yeah, back then people died kind of early. Well, he doesn't look too happy, does he? Think about the time frame. My granny used to say, and she went through the war and all, and so she used to say that people didn't smile in pictures back then because there wasn't a whole lot to smile about. So we are definitely fortunate and blessed in living in this world, and especially living here in America. Yeah. Okay, so I know, poor thing. But he's famous. He probably didn't get any money out of it, did he? It took a lot longer to take pictures. Oh, my gosh. And they were all black and white. Yes. Okay. Let me get, I think this would be a good time to take a break, if I can find my break. Find it. All right. So real quick, we're going to add all the resistances in a series. The same current flows through every part of the circuit. Okay. The sum of the voltage drops is going to equal the amount applied. That's Kirchhoff's second law. So whatever you apply to the circuit, to series circuit, then everything you get in the end should equal what you applied to it, which makes sense. You put in what you get out, so to speak. All right, how about give me a smiley face? I think I want to do, when we come back from break, I want to do a little bit more with series circuits before we go on because another one for website aids to build the circuit. Yes. Okay, so here's what we're going to do. I don't see my brakes picture. That's really weird.